Before we start, pay attention to one thing. This is something which is being introduced to those who are studying A2 for the very first time. This is something different. You have to pay attention to this phenomena that the output of one logic gate is being used as input of another logic gate. All right, output of one logic gate is being used as input of another. Over here, this is the same. Over here, this is the same, isn't it? So such type of circuits which are having their outputs as input are actually sequential circuits. All right, such type of circuits which are actually having their outputs as their input are sequential circuits. And what about those circuits which we actually studied till now, till half adder and full adder, where the input has nothing to do with the output of the same circuit? Yes, we may have input from another circuit's output, as we just had in full adder, that the output of first half adder was being used as input of the second half adder. But in this case, that is not the case. In this particular situation, same circuits output is being used as input of the same circuit itself. Such type of circuits which are having their inputs driven partially from their own outputs are called sequential circuits. So all those circuits which we have studied till now are called combinational circuits. Combination circuits or combination circuit. The output depends entirely on input. Input आई, process हुई, output चली गई, खत्म. We will now consider a second type of logic circuit known as sequential circuits. The output depends on the input values produced from the previous output values of the same circuit. All right. So what are combination circuits? The output depends entirely on the input. Input आई, process हुई, output हो गई. But then we have got sequential circuit. In this case, we have got sequential circuits. The output depends on the input produced from the previous output of the same circuit. Now, what is the use? The use is, first and foremost, use is to actually retain the data. As you can see, that data is then incarcerated, jailed inside the circuit. What goes out comes back in. So that might be this way, that data enters and then comes back, then enters, then comes back, then enters and then comes back. So the data is being trapped inside the circuit in a loop, and it is being retained until or unless first or this value is being changed. Only once you change this value or this value, then the data may be changed inside the loop, trapped loop of the circuit, or it can be changed or it can be retained. All right. So where do we use these sequential circuits? Mostly to retain the data, and then you can relate it. This is now computer's memory where you are actually keeping the data. So the memories are made up of these flip-flop circuits. If you do remember from your previous studies of O-level and AS level, when we studied static memories inside the processor, they were made of flip-flops. And the memories outside the processor, they were made up of the capacitors, which is RAM, dynamic. And static memory is being made up of SR flip-flops. Okay. So examples of sequential circuits include flip-flop circuits. Example of sequential circuits include flip-flop circuits. Now in this particular chapter, we will consider two types of flip-flop circuits, SR flip-flops and JK flip-flops. What you are looking at the moment are SR flip-flops. Okay, SR flip-flops consist of two crossed coupled NAND gates. Over here, they can equally be well produced from NOR gates. All right. So flip-flop circuits consist of two cross-coupled NAND gates. Cross-coupled. This output and input from the same circuit is referred to as the cross-coupled. NAND gates, they can equally be produced from NOR gates. The two outputs are labeled as, two inputs are labeled as S as in set and R as in reset. And two outputs are labeled as Q and Q naught. Q and Q naught. What does it mean? It means that the Q, whatever the Q, Q naught will be the reverse of it. Whatever the Q, Q naught will be reverse of it. Pay attention to their position. In NAND gate based SR flip-flop, Q stands on top, and in NOR gate based SR flip-flop circuits, Q stands on bottom. All right, so pay attention. In this particular lecture, we will use SR flip-flop circuits from NOR gates, as shown in here. Until now in exam, they have not asked questions related to the other type. So this is just for your knowledge. So we will be actually studying with respect to NOR gates, SR flip-flops with respect to NOR gates. Okay. Now let's call it. So I said that we will only be studying this chapter with NOR gates because that is the requirement of your syllabus. चलें, इस लाइट ने तो बेड़ा गर्क कर दिया यार. अच्छा जी, let's say this is gate X. I will refer to this as gate X, and this is gate Y. On the top it is gate X, and on the bottom I will call it XY. The output from the gate X is Q naught, and the output is from gate Y is Q. The output of the Q, the output of gate Y is Q, gate X is Q naught. ठीक है. अब X की जो input है उसको हम बोलते हैं S as set, और जो Y की input है उसको हम बोलते हैं R as reset. Remember, the other input is actually coming from the output of the other gate. Okay, so that we could trap the data. What is data? Was one single bit. One single bit is data. All right. So वो हम इस्तेमाल कर रहे हैं यहाँ पे. Okay. अब देखें, इसकी कुछ states होती हैं. स्टेट्स होती हैं. स्टेट का मतलब ये है कि इसकी कुछ शक्लें होंगी जो आपको याद रखनी है कि जब ये इनपुट होगी तो क्या आउटपुट होगी, जब आउटपुट होगी तो क्या इनपुट होगी. अच्छा, first of all that you need to remember is that you cannot change both bits together. All right, you cannot change both bits together. It would be a good idea if you could take few notes. You won't have so many things in the book or notes or somewhere. So I could not put all those things on this slide or the others. Sometimes you have to take it beta notes. So आप उसको ना थोड़ा थोड़ा सा जरा दिल लगा के अपने पास क्या नाम है लिख भी लिया करें बेटे. पता नहीं कंडीशंस कब तक चलेंगी और कितना आप उसको लाइट लेते हैं और फिर हम उसको कैसे रिवाइज करेंगे. We have no idea. What if they reopen schools in December? So we won't have any time to revise anything. Rather, we would have to actually depend on what we have studied, and we would have no time to revise it. Anyways, तो सबसे पहले क्या होता है जब कंप्यूटर स्टार्ट होता है. कंप्यूटर के स्टार्ट होते ही जो सिस्टम होता है, सिस्टम हर एक डेटा बिट को zero कर देता है. Means initially at the start all memories are filled with zeros. Now you need to pay attention to the fact that this one SR flip-flop circuit is responsible for one bit only. This is not the complete data. This is just one bit only. All right. So this flip-flop, SR flip-flop is holding up on one bit. One flip-flop is holding up for one bit. Let's say you have got memory of 1 GB. 1 GB means 1 billion byte. Every byte has 8 bits. It means that you have got 8 billion bits. Relatively, you would have 8 billion SR flip-flops because one single flip-flop is holding on one bit. Get the idea what I'm trying to imply over here? So, if you want to set, the term set is used for this NOR based flip-flop to have one trapped or one stored in one bit. So if you want to set this SR flip-flop, you have to have 1 in it. Now what actually happens that if you want to set, you will give 1 to S. Over here you can see that S is 1 and R would be 0. And remember, they both are not changed together. Only one is changed at a time. So R would be having input 0 and that will remain 0. All you have to do is to change S to 1. Once S has 1 and R has 0, the output will be at Q. System does not read output from Q naught. System only reads output from Q. All right. So why do we use Q naught? Because system would have no other way to find out that if the result is correct on Q or not. Only it would have just this idea that if Q is 1, Q naught will be 0. If Q is 0, Q naught will be 1. That would be the only way system would have an idea that the output is which is being produced by this particular bit based SR flip-flop, if it is correct or not. Now, how would system know that if the output is incorrect? Whenever there would be an error on this particular circuit, both Q and Q naught will be same. अगर Q और Q naught same हो जाते हैं तो इसका मतलब है आउटपुट में गड़बड़ है. Don't ask me question related to circuitry and electronics and all. This is the nature of it. We are not going to analyze these. We are just going to study the behavior of such circuits being computer students. If you study electronics or electric, then that would be the question why and when and how to work out the equations and all. Over here, you are just understanding these circuits. All right. So if you want to set the circuit, put 1 in S and R would already be 0. We don't change them both together. The output at Q will be the actual output and output at the Q naught would be the futile output, faltu output hogi that has system to do something with, but not we as user. Now, sequential circuits for retaining data on bit basis in memory, SR, and we are studying NOR based SR. If we like to now what happens that once you put 1 in S and there is 0 in R, You have then to retain the data. You have to latch it, latch. कुंडी लगा के बंद कर देना है उस data को. ये इस तरह नहीं होता. S would not continue. S would be just once one, and then it would discontinue. So what happens if you like to retain it? Then you would have to put 0 back in S. When R is already 0 and you put 0 in S, whatever the previous value that was in the circuit will be retained. उसको हम कहते हैं latch. So since you entered 1 before it, so system has 1. As soon as you put 0 in here, that 1 will be retained. Pay attention over here. Over here. Okay. So if you want to put 1 in this NOR based flip-flop, आप S में 1 डालेंगे, R would be 0, Q will become 1, Q naught will be 0. Then you would like to retain it. To keep it, then we will put 0 in S, so that will be then retained. Similarly, reset करना है. Reset means that you will put 1 in R. 1 in R and S would already be 0. As we have put already 0 over there, and now you want to reset. You want to reset, put 1 in R. As soon as you will put 1 in R, since S would already be 0, the data inside the circuit will become 0, and then you put 0 back in R to retain it. So mind it, when S is 1, R is 0, and you latch it, the circuit has got 1 saved in it. When S is 0, R is 1, and you latch it, circuit would have 0 in it. And at any given time, if they both are given ones, or they both are set together, there would be an error, and we call that error race. All right. In race, what happens that both Q and Q naught become 0. So if in NOR based SR flip-flop, both Q and Q naught are 0, this is said to be an error, and error is regarded as race. Race means that circuit is in a position which is not handleable, which cannot be handled. All right. So what do we expect now? We expect again 3 things. Number 1, the definition of SR flip-flop, the drawing of SR flip-flop circuit, and then the truth table of flip-flop circuit. But this truth table is not as the truth table that we make in combinational circuits. If you pay attention to the inputs of S and R, they are not as the inputs of combinational circuits. These are different. So these circuits will not be treated as the previous circuits that we have studied. These are different circuits. I hope that you are understanding. So if you want to set, S would be 1, R would be 0, Q would have then 1. If you want to retain that set, you would have to put 0 in S. So that would be latched out, whatever the previous value. If you like to keep 0 in the circuit, you would have to make R1 and S would be 0, and then you latch it out by having 0 in R. Whenever both are zeros, S and R, the data inside the circuit will be preserved. And if the both are ones, it means that this is an error which will result in Q and Q naught both as zeros, which is race. There's a question, can you explain latch again? Latch is basically whatever the previous data that you actually input to the circuit, you want to keep it. So you put 1 by having 1 in S, and then you make S 0. As soon as S is 0, R is 0, that 1 that was previously put in the circuit will be preserved, will be stored. Okay, that will be stored. So latch is actually keeping the data. S is entering the data to the circuit to keep it 1. And if you want to keep 0 in it, then S is 0 and R is 1. If you want to keep any of those, so what actually happens, the order would always be set, retain. Set, retain. Reset, retain. Retain is called latch. And if at any given point, if you put both inputs together, you would have an error. So we cannot put both inputs together. We have to put one by one. Now pay attention to, sir, why did you not use bridge at intersection? Okay, this is very good question, Peter. This is very good question. I have not used bridge over here. That bridging is C, optional. Now I'm telling you, you are in A2, that bridging is optional. All right. At O level and AS, we do insist about it so that you have an idea, but this is the usual way we make it. This is the usual way we make these circuits. If you like to bridge them, you can bridge them, but actually bridging is not done to show SR flip-flops. Okay, but they are certainly different lines. They have nothing to do with each other. They are intersecting, so you can put bridge on it. Doesn't matter, but this is not made that way. This is not made that way. This is optional now. Or whatever you feel like, you can put it, but this is the diagram. If you would look into books, if you would look over the internet, you would see they are being presented this way. All right, and this is up to you. How would you put it? No one would mind it with it. All right, all right, all right. Okay, so you got it. Now, if you pay attention to NAND base, although it is not part of the syllabus, it is not asked, but I felt like that you should know about it. In NAND base, things get reversed, and that becomes very much confusing. But you would have to pay attention. So retain is now with 1 and 1. 1 and 1 was error in NOR based SR flip-flop. In NAND based flip-flops, 1 is now retain, and 0 is now race or error. So over here in NOR based flip-flops, 1 and 1 produces what? 00, which is race. And in NAND based SR flip-flops, when you put both zeros, the result is 1 and 1 instead of output, and that is an error which is regarded as race. What was set in NOR based flip-flop is reset. In NAND based flip-flops, what was error in NOR based flip-flop, it is now retainership in NAND based flip-flop. So if you want to set, you would have to have 0 in set and 1 is reset. So reset is now set. It has now reversed. Please pay attention to it. This is now very important. Okay, so set is now reset. If you set, it will be resetted. Okay, see, S is 1, Q is 0. System reads from Q, not Q naught. And if you actually reset in terms of, if you put 1 in reset, then system would have 1 stored in it. That will be set. So set has become reset and reset has become set. Error has become latch now over here. So you would have to pay attention to it. Okay, now lastly, pay attention to these wordings: NOR active high, NOR active high, NOR active high. Okay, we studied von Neumann architecture. When we were studying von Neumann architecture, I did teach you about pulses which are being generated by the system clock, and whenever the pulse is high, the system starts performing another cycle of fetch, decode, execute operations. Okay, so it means that faster the signal or pulse which is being generated by the system clock, faster the computer is. Now that pulse is on and off, on and off, on and off, on and off, on and off. So when it is on, it is said to be high. When it is off, it is said to be low. Now what happens that few operations start when the pulse is high, and few operations start when the pulse is low. So it means that if you want to set, retain, reset, retain, set, retain, reset, retain, how and when that would happen? So when the system clock is high, NOR gate activates. Means when the pulse is 1, NOR gate set or reset. On the other hand, when the pulse is low, NAND gate activates. And it works vice versa. That you need to understand that NOR based active high circuit, which is NOR based SR flip-flops, starts working when the clock pulse is high. All right. So feel the A2 complications, heat. You need to remember these things. So NOR based SR flip-flops are actually NOR active high, and NAND gate based, NAND logic based SR flip-flops are NAND active low. All right. So now let's move on. These were SR flip-flop circuits. SR means set and reset. Now, as you can see, there are two constraints with these SR flip-flop circuits to retain the data. Those constraints are what? Number one, you cannot change both bits together. If you change, there is an error. That is the second constraint. That these circuits present error, number one. Number two, you cannot change both inputs together. To overcome these, one engineer named ZAK made an advanced form of these flip-flops, and they are then named after him, and it was JK, ZAK Kilby. Remember Sir Javed Khan, biology of it. वो भी हो सकता है JK. So Sir JK, by his name, remember that JK flip-flop. So ZAK Kilby actually upgraded these circuits, and he made it to the form which is here. Hold on. It is not updated. Yes, now. See, this is JK flip-flop circuits. What has happened that S is now called J and K is now called reset. Reset is called K. So J and K are actually S and R. But there is another inclusion of third input. See, system clock. System clock is never seen in terms of 1 and 0s, but highs and lows. All right. So inclusion of this system clock. Now you would see two new things in this JK flip-flop circuits. Number one, that one input is system clock. Number two, that one gate has got 3 inputs. Until now, in combinational circuits, we avoided having more than 2 inputs, and I always insisted that if there are 3 inputs, rather make 2 gates. If it is A and B and C, make 1 gate for A and B, and then take the output of A and B and then make another AND gate and mix it with C. So A and B in one, its output with another C in another, and then you get output for all 3. But over here, this is made this way. All right, this is the standard way of doing it. So please pay attention to the formation of this. Now, there are 2 things that you have to remember. Number one, now you would have an idea that why I have taught you SR flip-flop with NAND gate, because we were going to have that NAND logic based SR flip-flop incorporated in JK flip-flop. Over here you can see that if you pay attention to just this part, this is NAND logic based SR flip-flop, and whatever that is built on top of it is the addition made by JK. Now I want to revise or recall the memory trail related to the logic gate lecture that I gave last year. What I taught you, NAND and NOR gates are called universal gates for few things. Number one, they reduce the circuit by having NOT and AND gate or NOT or OR gate together. Number two, they have got this ability to make any circuit in the world. And number three, if you do remember, I taught you that time that they are used to make memories. So here we go. It is in front of you that these NAND and NOR gates are being used to create memories. This JK again will be holding 1 bit of memory, but this would have two most important things with it. You can change both J and K, set and reset together, and there would be no error. JK flip-flop circuits are an improvement over SR, as it by including another two NAND gates and high clock cycles, and that overcomes SR weaknesses. What are those weaknesses? Errors, limitation of individual input. So these two weaknesses or lacking of SR flip-flops are now lifted, now finished by inclusion of these two additional NAND gates over here. So what actually happened, that this would have no error, this would have no limitation of having one input at a time. You can change both inputs, and this would have another new state in it, and that is called toggle. What if you like, without first in SR, what you had to do, you have to set, then retain, then reset, then retain. You cannot go from set to reset because you would have to change both bits. In this case, that is possible. And number two, this only works when the clock cycle is high. So you can see this is low, this is high, this is low, this is high, this is low, this is high, this is low. So when the clock cycle is low, third input is not there. When third input is not there, anything else happens, doesn't work. There is no change to the data. When the clock cycle is high and you have changed J and K either together or individually, the result would be apparent in the circuit. So if J is 1 and K, means if you want to set, this is called set. If J is 1, K is 0 and clock cycle is high, then it sets the data. If J is 0, K is 1 and clock cycle is high, then it is reset. So you can go from set to reset, it's up to you. What if you like to toggle? You don't want to reset, you rather want to toggle. Toggle means that you don't care if it is 0, it becomes 1, and if it is 1, then you want to make it 0. If you just want to toggle it without being concerned, you have to remember this. अब इसमें अगर आपको लैच लगानी तो आप दोनों 0 डालेंगे तो लैच लग जाएगी. तो आपको सेट करके भी लैच लगाना है, रीसेट करके भी लैच लगाना है, टॉगल करके भी लैच लगाना है. लैच तो लगाना है क्योंकि मेमोरीज में लैच लगाए बगैर आपका काम नहीं बन सकता. Memories में you have to retain data. In order to retain the data, you would have to latch it. But the liberty of having a state toggled or going from set to reset directly is possible. And anything, see, if there are 3 inputs, there must be 2 to power 3 possibilities. But out of 2 to power 3, which is 8. 4 of the possibilities are with low clock cycle, so they are not being considered over here because low clock cycle does not have any effect on the circuit, and that is actually to prevent any error that might occur, and that works beautifully over here. So what are 3 advantages that we get? There is no error. We can go from one state to another without having this compulsion or restriction of having 1 bit changed, and you can toggle from one state to another. So if it is in one state, you toggle to another state and then latch it. If you want to directly reset from set, you do that directly by having 2 inputs and then latch it, whatever. Okay, so that's about it for JK flip-flops. I'll share these slides with you. RISC processor, RISC processors, क्या होते हैं? RISC processors is actually a term which is being used, reduced instruction set computer. All right, reduced instruction set computer, RISC processors. ठीक है जनाब. अब ये जो हमारे पास कंप्यूटर्स आजकल हैं, ये तो थोड़े से डिफरेंट हैं, ये पूरे रिस्क नहीं है, लेकिन समटाइम्स कुछ कंप्यूटर्स हमारे आसपास मौजूद होते हैं, स्पेशली जो पुराने वाले सेल फोन्स हैं वो रिस्क बेस्ड ही होते हैं. सो बेसिकली 3.3.5 RISC processors. So RISC and CISC processor. I'll show understanding of the difference between RISC and CISC processors. So early computers made use of von Neumann architecture that we studied in AS. Modern advances in computer technology have led to much more complex processor design, obviously. 2 basic philosophies have emerged over the last few years. Last few years, by saying last few years, I don't mean last few years as in 4, 5, 10 years. I mean that last few years means 4 decades, 3, 4 decades. Okay. 2 basic philosophies have emerged. Number 1, developers who want the emphasis to be on the hardware. Developers who want the emphasis over the hardware. Who are these developers who actually rely on hardware? These are gaming developers. These are operating system developers. These are those developers which are actually making hardware, or these making sophisticated hardware devices like robots, car systems, ECUs, and any gadget that is based on the control by the computer or microcontrollers, not those programs which you make for your string manipulation or accounting and journal system processing and office working, not those. So certainly if we are playing game, we are looking after their GPU concept. So that means that these games are based on hardware. So there is a clan of developers who want the emphasis to be on the hardware used. The hardware should be chosen to suit the high-end language development. Okay. And there are developers who want the emphasis to be on the software or the instruction set to be used. The philosophy is driven by ever faster execution time. आपको पता है कि जो supercomputer है, we don't count its speed in terms of megahertz or gigahertz or number of operations per second. Rather, we count its speed in terms of FLOPS, floating point operations per second, because anything which is hardware based must be actually stressing the hardware, and hardware is actually being judged by the result produced in terms of mathematics, not operations. Anyways, we will discuss that later. So let me revise. Early computers made use of von Neumann architecture. Modern devices in computer technology have led to much more complex processor design. The 2 basic philosophies have emerged over the last few years. Number 1, developers who want the emphasis to be on the hardware used. means the hardware should be chosen to suit the high level language development. Means first we will decide for hardware and then we will go for development. Secondly, developers who want the emphasis to be on the software to be used. This means that this philosophy is driven by ever faster execution times. Means that we actually develop and we expect that computer will execute it faster rather than paying attention to hardware. We pay attention to our work and then we actually depend on computer, how fast that computer. So the first philosophy is part of the group of processor architecture known as CISC. CISC is CISK. CISK over here. CISC. The first philosophy is part of a group of processor architectures known as CISC. Basically, IBM started the whole idea. IBM, now not known that much, but IBM started the idea. The second philosophy is part of the group of processor architectures called RISC, Reduced Instruction Set computers. Now, CISC processors architecture makes use of more internal instruction formats than RISC. I'll explain everything, just be with me, hold on. The design philosophy is to carry out a given task with as few lines of assembly code as possible. Remember that in the hardware, especially in this chapter, the instruction that we are referring to, instruction set that we are referring to, the language that we are referring to is nothing but assembly language. We are not paying any attention to any other language, just the assembly language, because that is the language of hardware. CISC, complex instruction set computer, processor architecture makes use of more internal instructions formats than RISC. The design philosophy is to carry out a given task with as few lines of assembly code as possible. Processor hardware must therefore be capable of handling more complex assembly code instructions. Essentially, CISC architecture is based on single complex instructions set which need to be converted by the processor into number of sub-instructions to carry out the required operation. I'll explain it further. For example, suppose we wish to add two numbers, A and B, load A and then add B, or that is RISC, two instructions, load A, which we have been doing, load A, add B. But if it is complex instruction set code, the instruction would be add A comma B. Add A comma B means there is just one instruction used and now we are relying on processor to do it its way. But in RISC, processor is not being relied on, that not being dependent over, rather what we do, we are dependent over our own understanding and the logic. We drive the whole car. In CISC, we just tell the computer, computer does it. This methodology leads to shorter coding that is called RISC, reduced instruction set code, but may actually lead to more work being carried out. RISC processors have fewer built-in instructions formats than CISC. This can lead to higher processor performance. The RISC design philosophy is built on the use of less complex instructions, which is done by breaking up the assembly code instruction into number of simple single cycle instructions. Ultimately, this means there is smaller but more optimized set of instructions than CISC. अब इस पे हम बात करते हैं. Please give me some time. Let me load the instruction set of RISC and CISC to make you understand it. अच्छा, अब आप देखें, number one, reduce instruction set code and complex instruction set code. Reduce instruction set code is strenuous for hardware, and complex instruction set code is strenuous for hardware, whereas reduce instruction set code is tough for programmers. ठीक है? So complex instruction set computer or code is CISC, reduced instruction set computer or code is RISC. If you pay attention to this code, that I hope that you would understand easily. This is LDM, load immediate 63. So 63 is being loaded. Then you added 64 to it. This is immediate. We are not referring to any memory, rather we are just, then product 29. Product means that whatever that is present at the address 29 will be added to the accumulator, will be multiplied with whatever is in accumulator. And what would be the accumulator? The addition of 63 and 64. Afterwards, whatever the result, that result, let's say R4 is the name of a register. The way we can name memory addresses, we have names of the processor registers as well. So there is a processor register called R4, register 4. So the content of the register 4 will be multiplied with the content of accumulator, and then whatever the result, that will be stored at location 23. So first of all, what happened? LDM 63, accumulator is loaded with 63. Number 2, then whatever the data in accumulator, that is 63, will be added with 64, and now the data is in accumulator, the result of addition of 63 and 64. Then whatever is present at the address 29 will be multiplied by the content of the accumulator, and the result would be in accumulator. Then afterwards over here, the content of register 4, R4, will be multiplied with the content of accumulator, and that will be stored in accumulator as well. And then whatever the result of accumulator will be stored at the address 23. So how many instructions are these? 1, 2, 3, 4, 5. This is reduced instruction set code, means easy instructions. Rather than writing a single instruction, we just wrote many instructions. Means that we have to write larger code to get the same thing. On contrary, if you look at RISC, CISC, if you look at CISC, so there is just one single instruction. That instruction says that multiply whatever in 23 and 29 with the 63 plus 64. And sorry, 23 is the storage. First thing in complex instruction code is the address of the location where you have to actually put the data back. Sorry. So now you can see this instruction. What will happen? 63 and 64 will be added first, and then they will be multiplied with 29. The result will be multiplied by the content of R4, and the whole thing is then saved to 23rd location, address 23 in memory. So how many instructions are there? 1. But that one instruction is complex. Why it is complex? Because now the programmer is expecting processor to do the rest. Over here, all processor has to do is just to follow one instruction at a time, and that's it, no more complexities. But over here, processor first has to figure out how to basically break up this one instruction into number of instructions, and then execute it. So what is happening? In RISC, the programmer is breaking the instructions and processor is just following it. In CISC, what is happening? That the programmer is giving one single complex instruction, and processor has now this duty to break that into number of instructions, and then these instructions will be executed by the processor one by one. So we can understand it easily by ourselves that the code in CISC is shorter because we have to write fewer lines, but the code in RISC is larger because we have to write more lines. Which is easier? It's up to the programmer, because these are two philosophies. we tend to look at things by our own perspective. So few of the programmers are basically in favor of CISC and few of the programmers are in favor of RISC. We as users, as the user of made program, we don't care about it, but when it is being programmed, when it is, we as the user of made programs, we as the user of the program which are downloadable and execution, are not very much concerned with it, but those who are making programs, developing programs, writing source code are actually concerned about it. Now, this is all old thing. Nowadays, the processors are hybrid. So sometimes they are using RISC, sometimes they are using CISC, but we have to study it in terms of what our syllabus require. So let's see. Now, I have put 4 points on each side. Number one, this is flexible instruction size. You need to remember in AS what happened that we studied that there is a bit size of the, which we call word size. There is a fixed bit sized system that is 32 bits, that is 64 bits. So the instruction that we write is actually having a ratio of 5 to 3. If you do remember, in 32 bits, 20 bits are allocated for opcode and 12 bits are for operand. And that is why we had this indirect addressing thing and all. If you do remember that, out of that compulsion, whatever the instruction that we write in a RISC, the operand should be of 12 bits. Over here, this is operand, and opcode should be of 20 bits. Okay, but in CISC, that limitation is lifted. Now you can write the instruction as big as required, as complex as required. The size is flexible. Why it is flexible? Because then processor will break it to the word size. Over here, we are given by that instruction set, which is for that processor word size. But over here, we are flexible. When we write more, processor breaks it itself. Over here, when we write, we have to write the way the processor wants it. So processor is doing itself, here we are doing itself. So this is flexible instructions size, over here it is fixed instruction size. Then whatever that we write is short code, over here whatever we write is larger code. We also discussed it. Over here compiler does less, because all compiler do is just convert this complex instruction to the binary form, which is still complex. Then the processor, this is the processor. Every processor has got a firmware. Now what is a firmware? Firmware is the software which is built in the processor by the manufacturer of the processor, and the first and foremost task of this firmware is to break a complex instruction into microcode. What is microcode? Microcode is making a complex instructions code in the form which is simpler instruction code. So when we do it, we call it RISC. When computer does it, computer calls it microcode. All right. So in RISC, what happens that you write complex code, compiler converts that complex code to the complex binary form, and then complex binary form passes through the firmware in the processor and turns into microcode. This is the additional strenuous work that processor has to do, and that work is not there in this RISC, because over here every instruction is in the exact size which is required by the processor. Our processor does is just to convert it. So over here compiler does less, over here compiler does more. Why compiler does more? Because there are more instructions. Here the number of instructions is less, so compiler, what compiler does? Compiler turns an assembly language instruction to its binary form. So when there are less number of instructions, less work for compiler. In RISC, there is high number of instructions, so more work for compiler. So that is why compiler does less. over here and compiler does more over here. Now this is favorable for high level languages. High level languages like Python, Visual Basic, Java, AI applications and all that we use nowadays. Just think about it. If we would have to write the simpler code, the program that you would have written, if they will be written in the form of assembly language program, you will be bitten by the length of the programs. So what actually happens that high level languages nowadays are not based on this. We have already studied that whatever that we do in high level languages is in short code, and if you convert it to the assembly language way, you would have to write the more code. So high level languages by default support complex instruction set code. So high level languages are built on top of complex instructions set code, whereas assembly language is built on reduced instruction set code. And that is, we know that whatever that you do, ultimately processor has to convert everything the way the assembly of that processor requires. Okay, so less effort by the programmer. Obviously programmer has to write less code. Over here the programmer has to write more code. So now we know that this CISC processor bears a firmware thing. The firmware breaks the complex instruction to the form which is easier to be executed by the processor, whereas in RISC the programmer itself writes the code that is simpler. Now processor does more. Over here processor does less, because processor would have the extra duty of converting the complex code to microcode. Over here high heat generation. Now this is another indication. So all those devices which have coolers in it, which have fans in it to cool down, those are made up of what? CISC. But you can see that these handheld devices like your iPads and tabs and cell phone, they do not have fan in it. So it means that these devices are more RISC oriented than CISC oriented. But if you have got a desktop and laptop, they might have fans outlets in it. They might have heat sinks in it. Nowadays, I'm not actually referring to the modern modern cell phone in terms of latest phone, because they have heat sink as well. And nowadays, hybrid means CISC and RISC, they both are being used by the processor nowadays. So let's just generalize it in common sense. In common sense, all those devices which are having ways to get rid of heat are basically CISC heavy, because processor is doing more. When the processor is doing more electrons are being flown. There is more friction. When there is more friction, there is more heat. When there is heat, you have to get rid of the heat, extend the heat. Whereas in RISC, processor is doing less, there is less heat. Less heat can be get rid of by just the chassis, or maybe the whatever casing that the device has. That casing would be enough to dismantle, or what do we say, not dismantle, to neutralize the heat and all. So requires cooling system. It does not require a cooling system. So all the desktops and laptops with the fans and all, they are actually having CISC, whereas over here casings are enough to pacify the heat. Bigger instruction set code. Bigger instruction set code means that you have more instructions. You have got so many instructions. And in RISC, you have got reduced instruction, means less instruction. What does it mean? Pay attention to this thing. This is very important. In CISC, this firmware converts the code to the reduced instruction set code. There is no control unit, and there is one separate circuit for every instruction. Whereas in CISC, there is a control unit, and that is responsible for the execution of the instructions. So all instructions are being executed by the control unit through its circuitry and all, but in RISC there is a separate circuit for every instruction. So having a separate circuit in for every instruction actually will put compulsion, because we cannot have enough number of instructions, because we have got the size restricted to the size of the processor. आप समझ रहे हैं ना कि अगर एक इंस्ट्रक्शन के साथ एक सर्किट है तो हमारे पास बस इतने ही सर्किट आ सकते हैं जितना कि हम उस प्रोसेसर के साइज में समा दें, उससे ज्यादा सर्किट्स नहीं आ सकते, जबकि RISC में there is no such limitation. Control unit is doing it, so you may have any number of instructions. सही हो गया. बिगर इंस्ट्रक्शन सेट मतलब हमारे पास ज्यादा इंस्ट्रक्शंस हैं, यहाँ पे कम इंस्ट्रक्शंस हैं. मेमोरी टू मेमोरी मींस देखें अभी क्या होता है कि अभी हम डेटा को जो है वो लेकर आते हैं मेमोरी से प्रोसेसर में. डेटा को हम लेकर आते हैं मेमोरी से प्रोसेसर में, और फिर हम उसको जो है प्रोसेस करते हैं, और फिर प्रोसेसर से लेकर जाते हैं वापस मेमोरी में रख देते हैं. तो ये क्या होता है जिसको हम कहते हैं RISC में जो हमने पढ़ा है वॉन न्यूमैन आर्किटेक्चर में, दैट first we have to load the data to accumulator with LDM, LDD, LDI, LDX, LDR, and then we process it in the registers, and then afterwards at the end we store it back to the memory. So this is called register to register working. Whereas in CISC what happens that we actually don't load and work and put it back. Rather we say that pick from this memory address and store in this memory address. So what is happening that we are over here, if you pay attention, pick from 29 from R4, take these two, and then result will be put back in the memory address mentioned over here at the start. So it means that this is memory to memory. So load and store operations are now built in. We don't have to actually do anything to load or store back. Rather, just all we have to do is to just write that pick from these memory locations and put back in this memory location, and whereas perform this operation on top of it. So get the idea. So this is called in CISC memory to memory. In RISC it is called register to register. All right. So now production of the microprocessor. Production of the microprocessor as Intel produces it, as in Qualcomm produces it, as in Samsung produces it. So when they produce CISC, obviously it is complex production. If it is complex production, it is expensive. Whereas RISC processors are easy to produce because the circuitry is there and it is simpler and all. So because of its simple method of production, they are cheaper. They are cheap as in less expensive. So last few points. Over here, single instruction is executed in multiple cycles. Now this is very important, that you have given one instruction in complex instruction set code, and then firmware will break it into number of microcodes or number of multiple instructions. So it means that one instruction will be executed in multiple cycles. What cycles? Fetch, decode, execute cycle. As you can see over here, in RISC we have got how many instructions there? 1, 2, 3, 4, 5. These 5 instructions will be executed one instruction in one cycle at a time, finished. Whereas this particular instruction will be, this is one instruction and it will be executed in 5 instruction cycles. Why? Because computer will first pass it through firmware to find the microcode. So one instruction of CISC takes many cycles to complete, whereas one instruction in CISC takes single cycle to complete. Then you would have your points to explain and all, but you need to pay attention to it. All right. And then uses control unit. I did explain it that CISC has got a control unit that does multi-clock cycles per instruction to complete the execution of the program, whereas In RISC, separate unit for every instruction. Whereas in RISC, there are separate unit for every instruction, and single clock cycle per instruction is used. And there are many types of instructions are available for memory addressing. And in RISC, there is just two types of instructions for load and instruction name. Not two types. There are like LDM, LDR, LDX, LDI, and what else? That's it. Four or five types. But over here, there are more than that. So we can refer to memory locations and register locations in more ways than those are available in RISC. All right, and then in CISC, micro program controller, and over here hardwired control unit. What does it mean that over here the control unit is actually micro programmed, firmware based? Over here it is hardwired control unit. That control unit only knows, let's don't call it control unit sometimes, rather it's just a unit that is controlling, that it takes one instruction and send it to the respective circuit to execute that instruction. Over here, there are no respective circuits. It is microprogrammed, so it does it itself. Pipelining is difficult, pipelining is easier. Now, what is pipelining? This would be related to another topic. Later, we will do it tomorrow and all. So,